For most of human history, the idea of emptiness seemed simple and intuitive. If all matter were removed from a region of space, what remained was assumed to be nothing at all. Ancient philosophers imagined emptiness as a passive void, a kind of non-existence that merely separated objects from one another. This intuition carried forward into classical physics, where space was treated as an empty container, and time as a silent background against which events unfolded. Matter moved, forces acted, and energy transferred. But the space in between was assumed to play no active role. It was there, but it did nothing. Isaac Newton's physics reinforced this view. In Newtonian mechanics, space was absolute and fixed, an unchanging stage that existed independently of the objects within it. If all particles were removed, space would still exist, perfectly empty and perfectly inert. Even later developments in classical electromagnetism did not fundamentally challenge this assumption. Fields such as electric and magnetic fields could exist in space, but the vacuum itself was still thought of as a neutral backdrop, incapable of producing energy or motion on its own. This classical idea of emptiness was deeply comforting because it aligned with everyday experience. When we empty a container, it appears to contain nothing. When a room is evacuated of air, it feels empty. There is no obvious sign of activity, no visible motion, no detectable substance. Physics grounded in observation and measurement naturally adopted this intuitive picture. Emptiness was defined by absence. Absence of matter, absence of energy, absence of structure. However, cracks in this world began to appear at the end of the 19th century. Certain experimental results refused to fit neatly into classical explanations. One of the most troubling was the behavior of radiation emitted by hot objects. Classical physics predicted that an idealized object should emit infinite energy at high frequencies, a prediction that was clearly unphysical and contradicted experimental evidence. This crisis hinted that something fundamental was missing from the classical understanding of energy and matter, and by extension from the understanding of emptiness itself. The breakthrough came when physicists realized that energy did not behave continuously at microscopic scales. Instead of flowing smoothly, energy appeared in discrete packets. This revelation did more than solve a technical problem. It undermined the foundations of classical physics. If energy itself was quantized, then the behavior of matter, radiation, and even empty space had to be reconsidered. The vacuum could no longer be treated as a featureless void, because the rules governing energy now imposed limits and constraints even in the absence of matter. As quantum theory developed, physicists began to understand that emptiness was governed by the same quantum laws as everything else. The notion that a system could be completely devoid of energy turned out to be incompatible with quantum mechanics. According to these new principles, every physical system has a lowest possible energy state, but that lowest state is not zero. Even when all removable energy is taken away, something remains. This residual energy does not belong to matter in the traditional sense. It belongs to the underlying fields that exist everywhere in space. This realization forced a radical reinterpretation of what nothing means. Empty space was no longer empty. It was filled with fields that could fluctuate, vibrate, and momentarily generate energy. These fluctuations were not caused by external disturbances. They were inherent to the nature of quantum reality. The vacuum, once thought to be silent and inert, was revealed to be restless and dynamic. The rejection of classical emptiness was further strengthened by the uncertainty principle, which placed fundamental limits on what can be known about physical systems. This principle implies that particles cannot be perfectly still, because perfect stillness would require exact knowledge of both position and momentum. As a result, motion never completely disappears, even in the most minimal energy state. This perpetual motion is not a failure of measurement or an experimental flaw. It is a built-in feature of the universe. As these ideas matured, physicists realized that the vacuum itself must obey the uncertainty principle. The fields that permeate space cannot be completely quiet. They must fluctuate even in the absence of particles. These fluctuations, what is zero-point energy, give rise to brief appearances of energy that vanish almost as soon as they form. Although these effects are subtle, they are not imaginary. Their consequences can be measured and have been confirmed experimentally. The collapse of the classical concept of emptiness marked one of the most profound shifts in scientific thought. It revealed that absence is not the same as inactivity, and that space itself has physical properties. Emptiness became something to be studied rather than assumed. Instead of asking what exists within space, physicists began asking what space itself contributes to reality. This shift also carried deep philosophical implications. If empty space is active, then reality is not built solely from solid objects interacting across a void. Instead, it emerges from an underlying fabric of fields and energies that exist everywhere, even where nothing seems to be present. What appears empty to our senses may at a deeper level be teeming with activity. In rejecting the classical idea of emptiness, physics did not merely add a new detail to its theories. It overturned a centuries-old assumption about the nature of existence. The vacuum was transformed from a passive nothingness into a dynamic foundation of the universe. This transformation set the stage for the concept of zero-point energy and opened the door to a new understanding of reality, one in which the universe is never truly empty, never completely still, and never as simple as it appears. The transformation of physics at the beginning of the 20th century did not happen suddenly or dramatically. It unfolded quietly through a single, almost reluctant idea introduced by Max Planck while he was attempting to solve a very specific problem. That problem concerned the way hot objects emit radiation, a phenomenon that classical physics believed it already understood. According to established theory, energy should flow continuously, allowing matter to absorb and emit radiation in smooth, uninterrupted amounts. Yet experiments stubbornly disagreed with these predictions. The mismatch was so severe that it threatened the internal consistency of classical physics itself. Planck approached the problem with deep respect for classical ideas and no intention of overturning them. His goal was not to revolutionize physics, but to find a mathematical trick that would make theory align with observation. In doing so, he made an assumption that would change science forever. He proposed that energy could only be exchanged in discrete units proportional to the frequency of radiation. This proportionality constant, later known as Planck's constant, imposed a fundamental limit on how small energy exchanges could be. Energy, once thought to be infinitely divisible, was suddenly granular. This assumption had an immediate and astonishing consequence. It meant that physical systems could no longer shed energy continuously down to absolute zero. Instead, they were forced to occupy specific energy states with a lowest possible state that could not be crossed. This lowest state did not correspond to zero energy. Even when a system had released all the energy it was allowed to give up, a small but unavoidable remainder persisted. This was the birth of the idea that nature forbids complete energetic emptiness. At first, this residual energy seemed confined to matter, atoms, oscillators, and vibrating systems. But as quantum theory expanded, physicists realized that Planck's insight applied far more broadly. The mathematical framework he introduced treated radiation and matter in symmetrical ways, implying that fields themselves must also obey quantization rules. If matter could not be fully drained of energy, neither could the electromagnetic field that permeates space. The implications were startling. Even in regions devoid of particles, energy must still exist. This marked the conceptual birth of the quantum vacuum. In classical physics, a vacuum was defined simply as the absence of matter and radiation. In the quantum framework emerging from Planck's work, a vacuum became the lowest energy state of a field. But because of quantization, this lowest state was not empty in the classical sense. It possessed an irreducible energy that could not be removed without violating the fundamental structure of quantum mechanics. Planck himself was deeply uneasy about the implications of his discovery. He viewed quantization as a formal device rather than a statement about reality. Yet other physicists soon realized its deeper meaning. Albert Einstein extended Planck's idea by applying quantization to light itself, proposing that light behaved as if it were made of particles. This further reinforced the idea that energy and fields were fundamentally discrete. The vacuum, therefore, could no longer be dismissed as nothingness. It was part of the same quantized universe as everything else. As quantum mechanics matured, the concept of zero-point energy became mathematically unavoidable. When physicists analyzed simple systems such as harmonic oscillators, they found that the equations always predicted a non-zero energy in the ground state. Attempts to eliminate this term led to contradictions or violations of the uncertainty principle. The mathematics was clear and uncompromising. Zero energy was not an allowed state. Quantum vacuum explained this insight extended naturally to quantum fields. Each point in space could be thought of as hosting oscillators corresponding to different fields. When all these oscillators were placed in their lowest energy states, the result was not emptiness, but a sea of minimal vibrations. The vacuum in this sense became a collective ground state of countless quantum oscillators, each contributing a tiny amount of energy. Together, these contributions formed what we now call vacuum energy. What made this idea especially revolutionary was that it assigned physical meaning to what had once been dismissed as background. The vacuum was no longer a passive stage, but an active participant in physical processes. Its energy could influence matter, modify forces, and even affect the structure of spacetime. This was a direct consequence of Planck's original quantization principle, extended beyond matter to the very fabric of space itself. The shift from classical emptiness to a quantum vacuum also forced physicists to rethink the meaning of temperature and absolute zero. In classical theory, absolute zero implied complete stillness and the total absence of energy. Quantum theory replaced this with a subtler picture. Absolute zero became the point at which systems reach their lowest allowed energy states, not a state of perfect rest. Even at this limit, motion and energy persist, encoded in zero-point fluctuations. The emergence of the quantum vacuum was not driven by philosophical speculation, but by mathematical necessity. Planck's constant set a fundamental scale for nature, and once that scale was accepted, the existence of vacuum energy followed inevitably. This is what makes the quantum vacuum so compelling. It is not an optional interpretation, but a requirement imposed by the structure of the theory itself. In retrospect, Planck's reluctant assumption reshaped the understanding of reality at the deepest level. By quantizing energy, he unknowingly revealed that emptiness is structured, that nothingness has a lowest energy state, and that the vacuum itself is a physical entity. The quantum vacuum stands as a direct descendant of Planck's original idea, embodying the realization that the universe cannot be completely drained of energy. Even when everything visible is removed, something fundamental remains, quietly vibrating beneath the surface of reality. The idea that nature possesses a lowest possible state may seem intuitive at first, but in classical physics, this notion did not exist in any meaningful way. Classical systems were assumed to be capable of losing energy continuously, approaching complete rest as their energy diminished. A pendulum could slow down indefinitely. A particle could eventually come to a halt, and a system cooled to absolute zero was expected to become perfectly still. Energy in this framework had no lower bound except zero itself, yet quantum theory overturned this assumption by revealing that zero is not an achievable endpoint. Instead, it exposed the existence of a minimum energy that cannot be removed from a system, no matter how extreme the conditions. This minimum energy is known as the ground state, and the energy associated with it is called zero-point energy. The term does not mean that the energy is literally zero. Rather, it refers to the energy present at the zero point of temperature. When a system has reached its lowest allowed energy level, it still retains this residual energy. It is not the result of thermal motion, external influence, or measurement error. It is intrinsic to the system's very existence. The reason for this lies in the quantized nature of energy. In quantum mechanics, systems are permitted to occupy only specific energy levels. These levels are not arbitrarily close together. They are separated by finite gaps determined by fundamental constants. As energy is removed from a system, it does not slide smoothly downward, but instead drops in discrete steps. Eventually, it reaches the lowest step available. At that point, no further energy can be extracted without destroying the system or violating the laws of quantum mechanics. A simple but powerful example of this principle is the quantum harmonic oscillator, a model that describes systems ranging from vibrating atoms to electromagnetic fields. When this system is analyzed using quantum equations, the lowest energy solution is never zero. Even in its ground state, the oscillator must retain a fixed amount of energy. This result is not an approximation or a technical artifact. It is exact and unavoidable. Attempts to force the energy to zero would require both position and momentum to be precisely defined, something forbidden by the uncertainty principle. The uncertainty principle provides deep insight into why zero-point energy exists. It states that certain pairs of physical properties, such as position and momentum, cannot both be known with perfect accuracy at the same time. If a particle were completely motionless, its momentum would be exactly zero, and if it were perfectly localized, its position would be precisely defined. Quantum mechanics prohibits this combination. Therefore, a particle can never be entirely at rest. Some degree of motion, and therefore energy, must always remain. This residual motion is not chaotic or random in the classical sense. It is structured, constrained, and governed by precise mathematical rules. Zero-point energy represents the most ordered form of motion allowed by quantum mechanics. It is the calmest possible state, yet it is not still. This subtle distinction marks a profound departure from classical intuition, where stillness and zero energy were synonymous. The concept of zero-point energy applies not only to particles but also to fields. In quantum field theory, every fundamental field is treated as a collection of oscillators spread throughout space. Each oscillator contributes a small amount of energy, even in its lowest state. When all fields are placed in their ground states, the result is a vacuum that is far from empty. Instead, it contains an enormous amount of distributed energy arising from these countless minimal oscillations. This energy does not behave like conventional energy stored in fuel or batteries. It cannot be easily extracted or concentrated because it represents the baseline energy of existence itself. Removing it would mean forcing the system into a state that quantum mechanics forbids. In this sense, zero-point energy defines the floor of reality. It establishes a limit below which energy cannot fall. The existence of a lowest possible energy state also has critical implications for stability. Without zero-point energy, matter would be fundamentally unstable. Electrons bound to atomic nuclei would lose energy continuously and collapse inward, causing atoms to shrink indefinitely. The presence of zero-point energy prevents this collapse by imposing a minimum motion that counteracts complete confinement. The solidity of matter and the persistence of atomic structure depend on this irreducible energy. Zero-point energy also reshapes the meaning of absolute zero. In classical thermodynamics, absolute zero was imagined as a state of perfect rest. Quantum mechanics redefines it as the temperature at which all systems occupy their ground states. Even at this limit, energy remains. Absolute zero does not eliminate motion. It reveals the lowest motion that nature allows. This insight has been confirmed by experiments in ultra-cold physics, where systems cooled to near absolute zero, virtual particles and fluctuations continue to exhibit quantum fluctuations. Philosophically, the idea that energy can never be fully removed challenges deeply rooted assumptions about nothingness and rest. It suggests that the universe is built in such a way that complete emptiness is impossible. Even the most minimal state of existence contains activity. Zero-point energy becomes a symbol of nature's refusal to allow total stillness. In this light, zero-point energy is not a mysterious add-on to physics, but a fundamental consequence of quantum laws. It arises inevitably from quantization and uncertainty, defining the lowest energy state that any system can attain. By revealing that the ground state is never truly empty, quantum theory replaces the classical dream of perfect rest with a more subtle and dynamic vision of reality, one in which motion persists at the deepest level, quietly sustaining the structure of the universe. One of the most unsettling discoveries of modern physics is that absolute stillness is impossible. No matter how much energy is removed from a system, motion never completely disappears. This conclusion does not arise from technological limitations or imperfect measurements. It is a direct consequence of one of the most fundamental principles of quantum mechanics. This principle establishes that certain physical quantities are inseparably linked, and that nature itself forbids their simultaneous precision. As a result, even at absolute zero temperature, where classical intuition expects total rest, motion remains unavoidable. At the heart of this idea lies the relationship between position and momentum. In classical physics, it is entirely reasonable to imagine a particle sitting perfectly still at a precise location. Its position is known exactly and its momentum is zero. Quantum mechanics, however, rejects this scenario outright. It states that the more precisely a particle's position is known, the less precisely its momentum can be known, and vice versa. This is not a statement about experimental error, but a statement about reality itself. If a particle were completely motionless, its momentum would be exactly zero, implying perfect knowledge of that quantity. To satisfy the uncertainty principle, this would require infinite uncertainty in its position, meaning the particle could be anywhere in the universe at once. Conversely, if the particle were confined to a precise location, its momentum would necessarily fluctuate. Either way, complete stillness is prohibited. The particle must possess some degree of motion, and therefore some energy at all times. This unavoidable motion persists even when temperature is reduced to its lowest possible value. Temperature is a measure of thermal motion, not of all motion. When a system is cooled, thermal energy is removed and random motion decreases. At absolute zero, thermal motion vanishes, but quantum motion does not. The uncertainty principle ensures that particles continue to jitter around their equilibrium positions even in the absence of heat. This residual activity is not thermal. It is quantum mechanical in origin. The consequences of this principle extend far beyond individual particles. Fields, which are the fundamental entities of modern physics, are also subject to uncertainty. A field cannot have both a precisely defined value and a precisely defined rate of change at the same time. This means that even when a field is in its lowest energy state, it must fluctuate. These fluctuations are not disturbances imposed from outside. They arise spontaneously from the quantum structure of the field itself. These persistent fluctuations give rise to what is often described as vacuum activity. Empty space, stripped of particles and radiation, still contains fields in their lowest energy states. Because of uncertainty, these fields cannot remain perfectly calm. They must vibrate, producing fleeting variations in energy. These variations manifest as momentary excitations that appear and disappear too quickly to be directly observed. Yet their effects can influence physical processes. The uncertainty principle also explains why zero-point energy is not merely a theoretical curiosity, but a necessity. If energy could be completely removed from a system, both position and momentum could be precisely defined, violating quantum rules. Zero-point energy serves as a safeguard, ensuring that uncertainty is always preserved. It represents the minimum amount of energy required to keep quantum systems consistent with their own laws. This principle has profound implications for the stability of matter. Consider electrons bound within atoms. If uncertainty did not exist, electrons could settle into fixed positions with zero momentum, collapsing into the nucleus. The uncertainty principle prevents this by enforcing a trade of confining an electron tightly increases its momentum uncertainty, which raises its energy and prevents collapse. The atom stabilizes at a finite size balanced by the competing demands of position and momentum uncertainty. The same logic applies to larger systems. In solids, atoms vibrate around their equilibrium positions even at absolute zero. These vibrations, known as zero-point motion, influence material properties such as elasticity, thermal conductivity, and even electrical behavior. In superfluid systems, zero-point motion plays a key role in enabling frictionless flow. What appears to be perfect stillness at the macroscopic level is at the microscopic level a ceaseless dance enforced by quantum law. The uncertainty principle also reshapes the meaning of energy conservation in subtle ways. While energy is conserved on average, quantum mechanics allows temporary fluctuations as long as they occur within time scales permitted by uncertainty relations. This permits brief borrowings of energy that give rise to transient phenomena. These effects do not violate conservation laws. They operate within the flexible framework that quantum uncertainty allows. From a philosophical perspective, the idea that motion is unavoidable challenges deeply held intuitions about rest and equilibrium. In everyday experience, stillness is associated with calm and stability. Quantum mechanics replaces this with a vision of stability arising from motion, not from its absence. Systems are stable, not because nothing happens, but because the motion that does happen is constrained and balanced. The realization that absolute rest is forbidden also alters our understanding of nothingness. Even in the deepest vacuum, uncertainty ensures activity. Space itself cannot be perfectly quiet. This insight bridges the gap between matter and emptiness, revealing them to be governed by the same principles. The universe does not allow static perfection. It favors dynamic balance. In the end, the uncertainty principle teaches that nature is fundamentally restless. Motion is not an accident or a temporary disturbance. It is a permanent feature of existence. Zero-point energy and vacuum fluctuations are simply expressions of this deeper truth. Even at absolute zero, the universe refuses to be still, maintaining a subtle invisible motion that underlies all structure and all stability. One of the most surprising outcomes of quantum physics is the realization that the vacuum is not calm or inert, but constantly active even in the complete absence of matter, energy and radiation in the classical sense. Space remains restless. This activity takes the form of tiny spontaneous variations in energy that occur everywhere and all the time. These are known as vacuum fluctuations, and they reveal that what we once called nothing is in fact a dynamic and ever-changing foundation of reality. Vacuum fluctuations arise directly from the quantum laws that govern all physical systems. As with particles and atoms, fields that permeate space are subject to uncertainty. A field cannot have a perfectly fixed value and a perfectly fixed rate of change at the same time. If a field were completely smooth and unchanging, it would violate this fundamental principle. As a result, even in its lowest possible energy state, a quantum field must fluctuate. These fluctuations are not caused by external disturbances or hidden forces. They occur spontaneously emerging from the quantum structure of the vacuum itself. At extremely small scales and over extremely short times, the energy of the vacuum can momentarily increase or decrease. These variations are fleeting, vanishing almost as soon as they appear. Yet, they are real enough to produce measurable effects. One way to visualize vacuum fluctuations is to imagine space as a tightly stretched fabric. Even when undisturbed, the fabric cannot remain perfectly smooth. Tiny ripples form and disappear continuously. In quantum physics, these ripples represent brief excitations of underlying fields. Although the analogy is imperfect, it captures the essential idea that restlessness is built into the fabric of space. These fluctuations are closely connected to the temporary appearance of particles. Quantum theory allows energy to fluctuate within limits set by uncertainty relations. When a fluctuation is large enough, it can briefly give rise to particle-like excitations that pop into existence and then vanish. These entities are often called virtual particles. They cannot be directly observed or isolated, but their influence can be detected through their interactions with real particles and fields. The presence of vacuum fluctuations has profound consequences for how forces behave. Electric and magnetic interactions, for example, are modified by the constant background activity of the vacuum. Charges placed in empty space do not interact across a static void. They interact through a fluctuating medium that slightly alters the strength and range of forces. This leads to subtle corrections in measurable quantities, confirming that vacuum activity is not merely theoretical. One of the most striking confirmations of vacuum fluctuations comes from the behavior of atoms. Even when isolated and cooled to extremely low temperatures, atoms exhibit shifts in their energy levels that cannot be explained by classical physics. These shifts arise because electrons interact with fluctuating electromagnetic fields in the vacuum. The vacuum, in effect, is energy in empty space, never silent, and atoms are constantly responding to its invisible vibrations. Vacuum fluctuations also play a crucial role in radiation processes. When an excited atom emits light, the emission is not triggered solely by the atom itself. The surrounding vacuum provides the fluctuations that stimulate the emission process. Without vacuum activity, certain types of radiation would not occur as they do. The vacuum actively participates in the exchange of energy between matter and fields. Another profound consequence of vacuum fluctuations is their effect on space and time at the smallest scales. At extremely short distances, the energy variations of the vacuum become so intense that they challenge the smooth picture of spacetime assumed in classical physics. Some theories suggest that spacetime itself may fluctuate, forming a constantly changing structure at the quantum level. Although this idea remains theoretical, it highlights how deeply vacuum fluctuations may be woven into the nature of reality. Despite their omnipresence, vacuum fluctuations do not lead to chaos or instability on macroscopic scales. Their effects average out, producing a stable and predictable world at large scales. This balance between microscopic restlessness and macroscopic order is one of the most remarkable features of quantum physics. The universe is noisy at its foundations but calm in its overall behavior. The concept of vacuum fluctuations forces a re-evaluation of what it means for something to exist. If empty space is constantly producing and absorbing energy fluctuations, then existence is not limited to tangible objects. Processes, interactions, and transient events become just as fundamental as particles. Reality becomes less about static things and more about continuous activity. In philosophical terms, vacuum fluctuations blur the boundary between being and non-being. Something arises momentarily from nothing only to dissolve back into it. Yet this nothing is structured, governed by laws and capable of producing real effects. The vacuum becomes a kind of creative ground not by intention or design, but by necessity. Ultimately, vacuum fluctuations reveal that the universe is never at rest. Even in the deepest emptiness, there is motion, energy, and change. These invisible vibrations are not anomalies or imperfections. They are essential features of quantum reality. By uncovering the restless nature of the vacuum, physics has shown that the most profound activity in the universe occurs where we once believed there was nothing at all. One of the most intriguing consequences of vacuum fluctuations is the brief and elusive appearance of entities known as virtual particles. These are not particles in the ordinary sense of stable objects that can be detected, isolated, or stored. Instead, they are temporary excitations of quantum fields that arise spontaneously and disappear almost immediately. Their existence challenges everyday notions of what it means for something to be real. Yet their effects are undeniable and measurable. Virtual particles emerge from the same quantum principles that govern zero-point energy and vacuum fluctuations. According to quantum mechanics, energy is never perfectly fixed over extremely short periods of time. The uncertainty principle allows small deviations in energy provided they occur within very brief time intervals. Within these limits, the vacuum can momentarily borrow energy, creating short-lived excitations that resemble particles. These excitations exist only fleetingly before the borrowed energy is returned and the particle vanishes. Unlike real particles, virtual particles cannot be directly observed. They do not appear in detectors as individual tracks, nor can they travel freely through space. Their existence is inferred indirectly through the effects they produce on measurable phenomena. In this sense, they are more like intermediaries than objects, acting as messengers of interaction rather than independent entities. Yet dismissing them as mere mathematical artifacts would be a mistake, because the predictions that rely on virtual particles match experimental results with astonishing precision. One of the clearest roles of virtual particles is in the transmission of forces. In modern physics, forces are understood as arising from interactions between fields. When two charged particles repel or attract each other, the interaction is described as being mediated by virtual excitations of the electromagnetic field. These virtual carriers are not particles flying back and forth in a classical sense, but quantum processes that transfer momentum and energy between interacting systems. Without them, the mathematical framework of quantum field theory would collapse. Virtual particles also influence the properties of real particles. An electron, for example, is not an isolated, immutable object. It is constantly interacting with the surrounding vacuum, exchanging virtual particles with it. This interaction slightly alters the electron's mass, charge, and magnetic properties. These changes are small but measurable, and they must be accounted for to achieve agreement between theory and experiment. The remarkable accuracy of these predictions serves as strong evidence that virtual particles reflect something physically meaningful about the vacuum. Another striking manifestation of virtual particles is their effect on atomic behavior. Electrons bound within atoms are influenced by the constant background activity of the vacuum. Virtual particles modify the electromagnetic field experienced by electrons, leading to tiny shifts in atomic energy levels. These shifts have been measured with extraordinary precision and match the predictions of quantum theory. The agreement between theory and observation confirms that virtual particles are not speculative ideas, but essential components of physical reality. Virtual particles also play a role in particle decay processes. Certain particles can transform into other particles through interactions that involve virtual intermediaries. Even when the intermediate particles cannot exist as real free entities due to energy constraints, they can still briefly appear as virtual states. These processes obey conservation laws on average, while temporarily exploiting the flexibility allowed by quantum uncertainty. Without virtual particles, many observed decay processes would be impossible to explain. It is important to emphasize that virtual particles do not violate energy conservation in any fundamental sense. While they appear to involve temporary energy imbalances, these imbalances occur within limits permitted by quantum laws. Energy conservation holds when measured over sufficiently long time scales. Virtual particles operate in a regime where classical intuition breaks down, but quantum rules remain intact and self-consistent. The existence of virtual particles also reshapes our understanding of emptiness. If empty space can give rise to particle-like excitations, then the vacuum is not merely a backdrop, but an active participant in physical processes. Space itself becomes a medium rich with potential activity, capable of influencing matter and radiation even when no real particles are present. The distinction between something and nothing becomes less clear, replaced by a spectrum of states governed by probability and fluctuation. From a conceptual standpoint, virtual particles force physicists to rethink what qualifies as real. Although they cannot be directly observed, their effects are as real as those produced by tangible objects. This challenges the idea that reality must consist only of things that can be seen or touched. In the quantum world, processes and interactions are just as fundamental as particles themselves. Virtual particles also highlight the deeply interconnected nature of the universe. No particle exists in isolation. Every particle is embedded in a web of interactions with the vacuum and with other fields. The vacuum is not an empty stage, but a dynamic environment that constantly interacts with everything within it. This interconnectedness helps explain why quantum theory is so successful in describing a wide range of phenomena using a unified framework. Ultimately, virtual particles reveal that the universe operates on principles far removed from everyday experience. Objects can appear without warning, exist briefly without being directly observed, and disappear without leaving conventional traces. Yet, these ephemeral entities play a crucial role in shaping the behavior of matter, energy, and forces. They are not imperfections or loopholes in the laws of physics, but natural consequences of a universe governed by quantum rules. In understanding virtual particles, we come closer to grasping the true nature of the quantum vacuum. It is not empty, not silent, and not inactive. It is a restless sea of potentiality where particles and interactions continually emerge and fade. Virtual particles stand as a powerful reminder that even the most invisible aspects of reality can exert profound influence on the universe we observe. At the heart of the quantum vacuum lies the electromagnetic field, a fundamental entity that exists everywhere in space, whether or not light is present. Classical physics treated this field as something that could be completely switched off in the absence of charges and radiation. Quantum physics revealed a very different picture. Even when no photons are present and all sources are removed, the electromagnetic field continues to vibrate. These vibrations are not signals, waves, or noise in the classical sense. They are intrinsic fluctuations that arise from the quantum nature of the field itself. In quantum theory, the electromagnetic field is not a smooth, continuous medium, but a collection of quantized modes, each behaving like a tiny oscillator. Every possible wavelength and direction corresponds to a mode that can store energy. When the field is excited, these modes contain photons. When the field is in its lowest energy state, no real photons are present. Yet each mode still retains a minimum amount of energy. This residual energy is the zero-point energy of the electromagnetic field. The existence of these ever-present vibrations is a direct consequence of the uncertainty principle. For each mode of the electromagnetic field, the field strength and its rate of change cannot both be precisely defined at the same time. If the field were completely motionless with no fluctuations at all, this principle would be violated. As a result, even in perfect darkness and absolute zero temperature, the electromagnetic field must fluctuate. These fluctuations do not produce light that can be seen or detected by ordinary instruments. They do not correspond to traveling waves or radiation carrying energy across space in the classical sense. Instead, they represent microscopic oscillations that remain localized and transient. The vacuum is therefore not illuminated, yet it is filled with invisible activity. Despite their subtlety, these electromagnetic vacuum vibrations have measurable effects. One of their most important roles is in shaping the behavior of charged particles. An electron moving through empty space is never truly isolated. It interacts continuously with the fluctuating electromagnetic field, exchanging energy and momentum at the scientific theories and experiments quantum level. These interactions slightly modify the electron's properties, such as its effective mass and magnetic behavior. The extraordinary agreement between theoretical predictions and experimental measurements confirms that these vacuum interactions are physically real. The electromagnetic vacuum also influences atomic structure. Electrons bound within atoms are immersed in fluctuating electromagnetic fields, even when the atom is isolated and cold. These fluctuations alter the energy levels of the atom in subtle ways. Precision experiments have detected these shifts with remarkable accuracy, providing strong evidence that vacuum vibrations are an unavoidable part of atomic reality. Another striking consequence of electromagnetic vacuum fluctuations is their effect on radiation processes. When an excited atom emits a photon, the emission is not triggered in isolation. The surrounding vacuum provides fluctuations that stimulate the emission. In this sense, the vacuum acts as an active partner in the interaction between matter and light. Without these vacuum vibrations, certain emission processes would occur differently or not at all. Electromagnetic vacuum fluctuations also play a crucial role in force phenomena. When objects are placed close together in a vacuum, the allowed modes of the electromagnetic field between them can be altered. This change in the pattern of vacuum vibrations produces measurable forces even in the absence of charges or currents. These forces arise purely from differences in vacuum energy, demonstrating that electromagnetic vibrations exert mechanical influence. The presence of electromagnetic vacuum energy raises profound questions about the energy content of empty space. When physicists calculate the total zero-point energy of all electromagnetic modes, the result is enormous. While this energy cannot be directly accessed or extracted using known methods, its theoretical magnitude suggests that the vacuum contains far more energy than all visible matter combined. This realization has fueled deep investigations into the role of vacuum energy in cosmology and the structure of spacetime. Importantly, electromagnetic vacuum vibrations do not lead to observable chaos or instability in everyday life. Their effects are typically tiny and balanced, averaging out over large scales. This is why classical physics remains such a good approximation for macroscopic phenomena. The vacuum's restless activity becomes significant only at very small scales or under carefully controlled experimental conditions. The idea that the electromagnetic field never truly rests challenges the classical association between darkness and emptiness. Even in the absence of light, space is alive with invisible oscillations. Darkness is not emptiness. It is simply the absence of photons above the vacuum level. Beneath this apparent calm lies a structured and energetic field. From a broader perspective, electromagnetic vacuum vibrations illustrate a central lesson of quantum physics. Fields, not particles, are the most fundamental components of reality. Particles emerge as excitations of fields, but the fields themselves persist even when unexcited. The vacuum is therefore not the absence of fields, but the state in which fields exist in their lowest energy configurations. In recognizing the electromagnetic field's perpetual vibrations, physics reveals a universe that is never truly quiet. Even the emptiest regions of space hum with invisible activity. These cosmic vibrations do not announce themselves loudly, but they quietly shape the behavior of matter, energy, and forces. The quantum vacuum sustained by electromagnetic zero-point energy stands as a reminder that reality is far richer and more dynamic than appearances suggest. The existence of zero-point energy and quantum vacuum fluctuations was initially a theoretical prediction, a consequence of quantum mechanics and the uncertainty principle. For decades, these ideas were treated with skepticism, often viewed as abstract mathematical constructs with little bearing on observable reality. However, experimental physics gradually provided evidence that the quantum vacuum is far from a theoretical artifact. Through careful and precise measurements, scientists were able to detect subtle effects that could only be explained by the restless activity of empty space, confirming that zero-point energy and vacuum fluctuations are physically real. One of the earliest and most significant confirmations came from spectroscopy, the study of the interaction between matter and electromagnetic radiation. Precision measurements of atomic energy levels revealed tiny shifts that could not be accounted for by classical physics. These shifts, later understood as the Lamb shift, arise because electrons interact with the fluctuating electromagnetic fields of the vacuum. The vacuum is not a passive backdrop. It actively perturbs the energy levels of atoms, producing effects that can be measured with extraordinary precision. The success of these predictions demonstrated that vacuum fluctuations are not just theoretical curiosities. They are measurable phenomena with real physical consequences. Another line of evidence comes from the study of spontaneous emission. Atoms in excited states emit photons and transition to lower energy states, a process that occurs even in complete isolation. Quantum theory revealed that this emission is stimulated by the vacuum itself. The electromagnetic vacuum provides fluctuations that interact with the atom, triggering the release of energy. Experimental observations confirm that the rate of spontaneous emission depends precisely on the structure of the vacuum, further validating the existence of zero-point energy and quantum field activity. Perhaps the most striking experimental evidence for vacuum energy is the Casimir effect, first predicted theoretically in 1948 by Rick Casimir. This phenomenon arises when two uncharged conducting plates are placed very close together in a vacuum. The plates experience an attractive force that cannot be explained by classical physics alone. The effect occurs because the vacuum between the plates allows fewer quantum fluctuations than the surrounding space, creating an imbalance in pressure that pushes the plates together. The Casimir effect has been measured with high precision in laboratory experiments, providing one of the most direct confirmations of the physical reality of vacuum fluctuations. Beyond the Casimir effect, modern experiments using ultra-cold systems, superconducting circuits, and cavity quantum electrodynamics have revealed additional manifestations of zero-point energy. For example, tiny shifts in superconducting energy levels observable in carefully designed circuits reflect interactions with vacuum fluctuations. Similarly, experiments trapping atoms in optical cavities show that the vacuum can modify atomic behavior, influencing emission rates and energy transitions. Each of these observations reinforces the conclusion that the vacuum is not empty. It is a dynamic and influential participant in physical processes. High-energy physics further demonstrates the reality of vacuum energy in particle accelerators. Collisions between particles produce effects that are consistent only if the vacuum is treated as an active field. Virtual particles which briefly pop into and out of existence contribute to force interactions and scattering amplitudes. Experiments confirm that these interactions match the predictions of quantum field theory to astonishing accuracy. Without acknowledging the reality of the vacuum, these results would be inexplicable. Even in cosmology, indirect evidence points to the influence of vacuum energy. Observations of the universe's accelerated expansion suggest the presence of a mysterious form of energy permeating space often associated with the vacuum itself. While the connection between zero-point energy and dark energy remains a topic of active research, it demonstrates that vacuum energy is not a confined laboratory curiosity, but potentially a key component of the cosmos. Experimental evidence also underscores the quantitative importance of vacuum energy. Calculations of zero-point energy, while theoretically immense, have measurable consequences in small-scale systems. Precision experiments have confirmed that energy shifts due to vacuum interactions match predictions from quantum theory, validating the idea that the vacuum has a real calculable energy density. This bridges the gap between abstract mathematics and observable reality, showing that even empty space has a tangible presence. The recognition of zero-point energy as experimentally verified transformed the way physicists understand the universe. It became clear that the vacuum is not a passive backdrop, but an active field with measurable consequences. It interacts with matter, influences atomic behavior, and mediates forces, revealing a profound connection between empty space and observable phenomena. This realization also highlighted the power of quantum theory, which predicted these effects long before experimental confirmation, illustrating the deep predictive capacity of the mathematical framework. Furthermore, experimental confirmation of zero-point energy has practical implications. Technologies such as superconducting qubits, ultra-precise sensors, and nanomechanical systems operate in regimes where vacuum fluctuations cannot be ignored. Understanding the vacuum's influence allows engineers to design devices that exploit or mitigate these effects, demonstrating that the quantum vacuum is not merely a curiosity, but a factor in cutting-edge technology. Finally, the experimental reality of vacuum energy invites philosophical reflection. It forces a reconsideration of what emptiness truly means. Space is not a void, but a medium filled with activity, a seething backdrop that influences the very behavior of matter and radiation. The universe, even at its most barren, is never completely empty. Experimental evidence has transformed vacuum energy from a speculative idea into a concrete component of physical reality, reshaping our understanding of the fundamental nature of existence. In conclusion, decades of careful observation and precise experimentation have confirmed that zero-point energy and quantum vacuum fluctuations are real measurable phenomena. From atomic spectroscopy and spontaneous emission to the Casimir effect in high-energy particle interactions, the evidence consistently points to a vacuum that is active, energetic, and fundamentally intertwined with the behavior of matter and energy. Far from being empty, the vacuum is a dynamic, restless, an essential part of the universe whose influence can be detected, measured, and even harnessed in modern technology. Through these experiments, the abstract predictions of quantum theory have become undeniable facts of physical reality. Among the most striking demonstrations of the quantum vacuum's physical reality is a phenomenon known as the Casimir effect, predicted in 1948 by the Dutch physicist Rick Casimir. This effect provides one of the clearest pieces of experimental evidence that empty space is far from empty. Unlike many quantum phenomena which are subtle and require complex apparatus to detect, the Casimir effect produces a tangible, measurable force, a force that emerges purely from the restless activity of the vacuum. Its discovery and confirmation revolutionized our understanding of what the vacuum can do, and how the invisible energy of empty space can manifest in the observable world. The Casimir effect arises from the properties of the electromagnetic vacuum, the sea of zero-point energy that exists everywhere in space. Even in the absence of photons and matter, the electromagnetic field continues to fluctuate as required by quantum mechanics. These fluctuations occur at all wavelengths, producing tiny oscillations throughout the vacuum. When objects such as conductive plates are placed close together, the allowed wavelengths of these fluctuations become constrained. Only certain modes of vibration can fit between the plates, while the full spectrum of modes exists in the surrounding space. This imbalance creates a measurable pressure. The plates are pushed together by the difference in vacuum energy inside and outside the gap. At first glance, the idea that empty space can generate a force may seem impossible. Classical physics teaches that forces arise from interactions between objects, not from nothing. In the quantum world, however, the vacuum is not nothing. It is a dynamic entity filled with fluctuating fields and ephemeral excitations. The Casimir effect is a striking manifestation of this hidden activity, converting invisible fluctuations into a mechanical force that can be measured with extraordinary precision. It demonstrates unequivocally that the vacuum has structure, energy, and physical influence. Experimental verification of the Casimir effect has evolved over decades. Early experiments faced enormous challenges because the forces involved are extremely small, requiring precise alignment of surfaces and sensitive detection methods. Nonetheless, by the late 20th century, advances in instrumentation allowed scientists to measure the attractive force between plates separated by distances on the order of nanome. The results matched theoretical predictions with remarkable accuracy, confirming that vacuum fluctuations were responsible for the observed effect. This agreement between theory and experiment cemented the Casimir effect as one of the most compelling pieces of evidence for zero-point energy. The implications of the Casimir effect extend beyond a laboratory curiosity. It shows that the vacuum can exert mechanical influence on macroscopic objects. In principle, this means that even seemingly empty space can participate in physical interactions. The effect is strongest at very short distances, where the density of allowed vacuum modes is highly constrained, but it persists at larger scales as well, albeit at more weakly. It demonstrates that the vacuum is not an inert backdrop, but an active medium capable of transmitting forces. The Casimir effect also provides insight into the relationship between quantum fluctuations and energy. The force arises because the vacuum energy inside the gap between the plates is lower than the vacuum energy outside. In other words, the vacuum itself has an energy density that can vary with boundary conditions. By constraining the field in a specific region, one can manipulate the local vacuum energy, creating measurable consequences. This principle hints at a profound connection between geometry, boundary conditions, and the energy content of space. A connection that resonates with ideas in modern cosmology and quantum field theory. Beyond its conceptual significance, the Casimir effect has practical applications and implications for technology in nanotechnology and microelectromechanical systems. MEMS. The Casimir force becomes a significant factor when components are separated by tiny distances. Engineers must account for the effect to prevent unwanted sticking or interference between parts. At the same time, researchers explore the possibility of harnessing vacuum forces for new types of nanoscale devices. While the idea of extracting usable energy from the vacuum remains speculative and constrained by quantum laws, the Casimir effect demonstrates that the vacuum is far from passive and can have practical consequences at the microscopic scale. The Casimir effect also illuminates the interplay between classical and quantum ideas. In classical physics, two uncharged, perfectly conducting plates should not interact if they are electrically neutral. Yet, the Casimir effect shows that quantum principles, specifically the fluctuations of the vacuum, can induce a force where none is expected classically. This highlights a broader lesson of quantum mechanics. The vacuum, far from being a void, is an active participant in reality, capable of producing phenomena that defy classical intuition. On a more fundamental level, the Casimir effect connects the physics of the very small to the structure of the universe itself. It illustrates how zero-point energy, though often invisible and subtle, can have real measurable consequences. In cosmology, similar principles suggest that vacuum energy may influence the expansion of the universe, contributing to the mysterious phenomenon known as dark energy. The Casimir effect, while a laboratory-scale phenomenon, provides a tangible example of how vacuum energy can manifest in ways that are both predictable and significant. The effect also deepens philosophical understanding of the nature of nothing. The vacuum is not merely empty space. It is a dynamic structured entity that can influence matter. Forces can arise not from objects or particles alone, but from the constraints imposed on the underlying quantum fields. In this sense, the Casimir effect transforms our understanding of emptiness, showing that even where there is no matter, no light, and no classical energy, reality remains active and responsive. In addition to the original setup with parallel plates, variations of the Casimir effect have been explored, including configurations with spheres, cylinders, and more complex geometries. Each variation demonstrates that the effect depends sensitively on shape, orientation, and boundary conditions, reinforcing the idea that the vacuum's energy is not uniform, but responsive to context. These studies continue to provide insight into the properties of quantum fields and their interactions with matter. Ultimately, the Casimir effect stands as a remarkable bridge between theory and experiment. It confirms that the quantum vacuum is real, energetic, and influential by converting invisible fluctuations into measurable forces. It transforms the abstract concept of zero-point energy into a tangible phenomenon. It reminds us that reality is far richer than it appears. Even the emptiest regions of space are alive with activity, exerting forces, shaping matter, and revealing the profound structure of universe at its most fundamental level. The exploration of vacuum energy reveals an astonishing feature of the universe. Even what appears to be empty space is teeming with subtle activity. One of the most profound consequences of this realization is that the quantum vacuum has measurable physical effects on matter and energy. These effects arise not from classical forces or particles, but from the underlying fluctuations of quantum fields. They demonstrate that the vacuum is not simply a passive backdrop for the universe, but an active participant in its dynamics, influencing systems in ways that are both unexpected and experimentally observable. One of the clearest examples of the vacuum's influence is its effect on atomic and molecular systems. Atoms are never truly isolated, even in a vacuum. Electrons within atoms interact continuously with the fluctuating electromagnetic field of empty space. These interactions subtly shift the energy levels of electrons, leading to measurable phenomena such as the Lamb shift. First measured in the mid-10th century, the Lamb shift provided direct confirmation that vacuum fluctuations affect the behavior of matter. It showed that the electromagnetic vacuum is not silent. It can influence atomic spectra, and by extension the properties of all matter that depends on atomic structure. These interactions extend beyond individual atoms. Molecules and larger systems are similarly affected by the ever-present activity of the vacuum. Tiny shifts in energy levels, subtle changes in force interactions, and small perturbations in behavior are all consequences of quantum fluctuations. These effects are usually extremely small, but modern experimental techniques allow them to be measured with remarkable precision. In essence, the vacuum serves as a hidden medium that subtly shapes the properties of matter on both microscopic and macroscopic scales. The vacuum also plays a critical role in force mediation. Classical physics attributes forces to direct interactions between objects such as contact or electromagnetic attraction and repulsion. Quantum mechanics, however, reveals that forces are often transmitted through the exchange of virtual particles arising from the vacuum. For instance, the electromagnetic force between charged particles can be described as the result of virtual photons exchanged through the vacuum. These photons are not real in the conventional sense, but their interactions produce the forces that govern particle behavior. This demonstrates that even empty space is integral to the mechanisms by which forces operate. Another dramatic consequence of vacuum energy is found in the Casimir effect. When conductive plates are brought extremely close together in a vacuum, they experience an attractive force due entirely to the differences in vacuum fluctuations between the plates and surrounding space. The Casimir effect provides direct measurable evidence that the vacuum can exert mechanical influence. It shows that zero-point energy is not a purely theoretical construct, but a real source of interaction between material objects. This effect has been confirmed experimentally and remains one of the clearest demonstrations that the vacuum is active, not passive. Vacuum energy also affects radiation processes. The emission and absorption of photons by atoms and molecules are influenced by the surrounding vacuum. Even in the absence of external stimuli, the vacuum's fluctuations can trigger spontaneous emission, altering the rates and characteristics of radiative transitions. In this way, the vacuum acts as a silent participant in processes that classical physics would attribute solely to the matter involved. The activity of the vacuum is therefore an essential factor in understanding the behavior of light and matter at the quantum level. These effects are not limited to small systems. In high-energy physics, interactions between fundamental particles are profoundly shaped by vacuum fluctuations. Virtual particles that briefly emerge from the vacuum contribute to scattering processes, decay rates, and particle interactions. Experiments at particle accelerators confirm that these effects are real and measurable, matching the precise predictions of quantum field theory. The vacuum, though invisible, is an active component of the interactions that structure the subatomic world. The influence of vacuum energy also extends to condensed matter systems. Superfluids and superconductors, for example, exhibit behaviors that cannot be fully understood without accounting for zero-point energy. The fluctuations of the vacuum contribute to the stability and properties of these systems, affecting phenomena such as frictionless flow and quantized magnetic flux. In such systems, vacuum fluctuations are not just theoretical curiosities, they have tangible consequences that define the material's behavior. The realization that vacuum energy has observable effects has profound implications for technology. Modern experiments and devices, from ultra-precise atomic clocks to nanoscale mechanical systems, must account for the vacuum's influence. In nanotechnology and micro-electromechanical systems, the forces arising from zero-point energy can alter device behavior, sometimes causing components to attract or repel each other unexpectedly. Understanding and controlling these effects is essential for engineering at extremely small scales, making the vacuum a practical consideration as well as a theoretical one. Philosophically, the vacuum's influence challenges traditional notions of emptiness. Space is not merely a backdrop or container for matter, it is an active participant in reality. Even in the absence of matter, the vacuum exerts forces, modifies energy levels, and mediates interactions. What appears empty to the senses is in fact a dynamic and structured medium that underlies the behavior of all matter and energy. The universe, therefore, is never truly empty. Even in its most seemingly barren regions, activity persists, subtle yet consequential. In conclusion, vacuum energy exerts profound effects on physical systems, demonstrating that empty space is far from passive. From atomic energy shifts and spontaneous emission to force mediation and the Casimir effect, the quantum vacuum actively shapes matter and radiation. Its fluctuations influence interactions at every scale from subatomic particles to nanoscale devices, confirming that the vacuum is a dynamic and essential component of reality. By revealing that empty space itself participates in physical processes, the study of vacuum energy transforms our understanding of the universe, showing that the most fundamental levels of reality are alive with invisible yet measurable activity. The concept of vacuum energy challenges our deepest intuitions about space, matter, and reality. What was once thought of as empty space, devoid of matter and devoid of activity, has been revealed by quantum mechanics to be a dynamic and restless medium teeming with invisible fluctuations. These fluctuations are not simply theoretical curiosities. They have measurable consequences that affect everything from the behavior of individual atoms to the forces between macroscopic objects. Understanding the pervasive influence of vacuum energy requires examining how these invisible oscillations interact with matter and influence physical processes. At the foundation of these phenomena is the recognition that quantum fields which exist throughout space cannot be completely at rest. Each field is composed of countless oscilli modes, each capable of storing energy. Even when a field is in its lowest energy configuration, the vacuum state, each mode retains a minimal amount of energy. This energy, known as zero-point energy, ensures that the vacuum is never truly still. Consequently, the vacuum is constantly fluctuating, with energy rising and falling in a manner dictated by the uncertainty principle of quantum mechanics. These fluctuations have immediate and profound effects on particles and atoms. Electrons in atoms, for instance, are not isolated from the vacuum. They interact continuously with the fluctuating electromagnetic field, which slightly perturbs their energy levels. The Lamb shift, an experimentally observed change in atomic energy levels, arises precisely from these interactions. Its precise measurement confirmed that the vacuum is not a passive void, but an active participant in atomic processes. At a deeper level, this demonstrates that matter cannot be fully separated from the vacuum. The two are inherently interconnected. Beyond influencing individual particles, vacuum energy can generate measurable forces between objects. This is most famously illustrated by the Casimir effect, in which two uncharged conducting plates placed very close together in a vacuum experience an attractive force. The effect arises because the presence of the plates alters the spectrum of allowable electromagnetic fluctuations between them compared to the surrounding space. Fewer modes can exist between the plates, creating an imbalance that pushes them together. The Casimir effect exemplifies how point energy is not confined to abstract theory, but manifests physically in the laboratory. The influence of vacuum fluctuations extends even further. Virtual particles which briefly emerge and disappear from the vacuum mediate forces between fundamental particles. These transient entities cannot be directly observed, yet their effects are evident in scattering experiments, decay rates, and particle interactions in high-energy physics. The predictions of quantum field theory regarding these interactions match experimental results with remarkable accuracy, confirming the reality of the vacuum's restless energy. These virtual particles highlight that the vacuum is not merely a passive stage for matter to occupy, but an active medium that participates in the fundamental interactions of nature. In condensed matter systems, zero-point energy also plays a critical role. Superfluids and superconductors, for example, exhibit properties that are impossible to explain without accounting for vacuum fluctuations. The stability and behavior of these systems depend on the subtle effects of zero-point motion, which influence the dynamics of atoms and electrons even at extremely low temperatures. Similarly, in nanotechnology and micro-electromechanical systems, vacuum forces arising from fluctuations can cause components to attract or repel each other, necessitating careful engineering. Ensure proper functionality. These examples illustrate that the effects of vacuum energy are both ubiquitous and practically relevant. Vacuum energy also has cosmological implications. The energy of the vacuum contributes to the overall energy density of the universe, potentially playing a role in cosmic expansion. The observed acceleration of the universe's expansion is often attributed to a form of vacuum energy known as dark energy. While the precise connection between zero-point energy and cosmological phenomena remains a topic of active research, it underscores the principle that the vacuum is far from empty. It has measurable consequences, not only in the laboratory, but on the scale of galaxies and the entire universe. Philosophically, the existence of vacuum energy forces a re-evaluation of what empty space truly means. Classical intuition treats a vacuum as a void, a complete absence of matter, radiation, and energy. Quantum mechanics reveals that such a state does not exist in nature. Even the lowest possible energy state contains fluctuations, motion, and potentiality. The universe, therefore, is never truly empty. Even the most barren regions of space are alive with invisible activity, a hum of energy that underpins the behavior of everything within it. The presence of vacuum energy also reveals the deep interconnectedness of the universe. Particles, fields, and space are not independent entities, but components of a unified quantum reality. A particle cannot exist without interacting with the vacuum, and forces arise from fluctuations within the fields that permeate space. The vacuum acts as a medium linking matter and energy, providing a subtle but pervasive influence on all physical phenomena. Experimental verification continues to strengthen our understanding of vacuum energy. High-precision measurements of atomic transitions, cavity quantum electrodynamics experiments, and nanoscale force measurements consistently confirm the effects predicted by theory. Each observation reinforces the principle that the vacuum is a dynamic energetic substrate underlying the universe. These results demonstrate that the abstract concepts of quantum mechanics have concrete observable manifestations, and they bridge the gap between theory and reality. At a practical level, recognizing the influence of vacuum energy opens new possibilities for technology. Understanding and controlling the effects of vacuum fluctuations is essential for the design of quantum devices, sensors, and nanoscale machines. While harnessing vacuum energy on a large scale remains speculative, its influence on the microscopic world is undeniable, guiding innovations in quantum computing, precision measurement, and materials science. In conclusion, the quantum vacuum is a restless and dynamic medium whose influence pervades the universe. Its zero-point energy affects atoms, mediates forces, shapes material behavior, and even potentially drives cosmological expansion. Experimental evidence confirms that the vacuum is far from empty, revealing a reality in which space itself is active and structured. This recognition transforms our understanding of the universe, showing that what we once considered nothing is in fact a foundational and energetic part of existence, quietly shaping the behavior of all matter and energy. One of the most fascinating aspects of the quantum vacuum is its potential role as a reservoir of energy, a concept that has captured the imagination of both physicists and the public alike. While zero-point energy has been rigorously defined and observed in controlled experiments, the idea that it could be harnessed or influence larger systems presents both profound theoretical implications and practical challenges. Understanding this potential requires a careful examination of how vacuum energy manifests, how it interacts with matter, and why its extraction remains fundamentally constrained by the laws of quantum mechanics. At its core, zero energy represents the irreducible minimum of energy present in any quantum system. Even in the absence of heat, light, or other classical forms of energy, quantum fluctuations ensure that motion persists. Particles cannot come to complete rest, fields cannot become perfectly still, and the vacuum itself is never devoid of activity. This residual energy exists everywhere, permeating all space, and is present in both microscopic systems like atoms and macroscopic contexts such as the electromagnetic vacuum between objects. The idea that this energy could be tapped for practical use is appealing, but the reality is far more subtle. The energy is intrinsic to the quantum state of the system, meaning it cannot simply be extracted without altering the system itself. Attempts to remove or concentrate zero-point energy in a controlled way confront fundamental constraints imposed by quantum mechanics, including the uncertainty principle. Since the vacuum's energy is a baseline requirement of quantum fields, extracting it would require forcing fields or particles into states that violate these principles, something that is currently impossible according to our understanding of physics. Nevertheless, zero energy does have observable effects that can be utilized indirectly. For example, the Casimir effect demonstrates that the vacuum can exert forces on macroscopic objects due to differences in vacuum energy between regions of space. In nanotechnology, this effect must be accounted for when designing micro-electromechanical systems, as the vacuum can cause components to attract or repel unexpectedly. While not a direct method of extracting energy, this illustrates that the vacuum's fluctuations have tangible manipulable consequences. Another avenue in which zero-point energy influences physical systems is through spontaneous emission and atomic interactions. Atoms interact with the fluctuating electromagnetic field of the vacuum, affecting emission rates, energy levels, and transition probabilities. In principle, understanding and controlling these interactions could allow scientists to influence quantum processes in ways that are technologically valuable, such as enhancing the performance of lasers, sensors, and quantum devices. Here the vacuum acts as a participatory medium, guiding behavior at a quantum level, even though the energy itself cannot be removed or consumed in the classical sense. High-energy physics also provides insight into the potential applications and limits of vacuum energy. In particle accelerators, virtual particles and vacuum fluctuations mediate fundamental interactions influencing forces, decay rates, and scattering events. While the energy associated with these fluctuations is immense when summed across all possible modes, it is distributed in such a way that it cannot be harnessed as a coherent, usable energy source. The fluctuations are inherently ephemeral, appearing and disappearing within time scales set by quantum uncertainty, making them resistant to conventional energy extraction. Cosmology further complicates the picture. The universe's accelerated expansion suggests the presence of a pervasive energy, often associated with the vacuum, that influences the dynamics of spacetime itself, known as dark energy. This phenomenon shares conceptual similarities with zero-point energy. While it demonstrates that the vacuum has real large-scale effects, it also emphasizes the difficulty of harnessing such energy, as it is fundamentally tied to the structure of spacetime and operates on cosmic scales rather than local controllable environments. Despite these constraints, zero energy remains a rich area of theoretical exploration. Physicists consider how modifications of vacuum states could lead to novel phenomena such as changes in force interactions, altered decay rates, or engineered fluctuations in confined systems. Concepts such as dynamic Casimir effects, where moving boundaries can convert vacuum fluctuations into real photons, demonstrate that while energy cannot be extracted freely, it can be influenced and transformed under carefully controlled conditions. These effects underscore that the vacuum is not static. Its fluctuations can be shaped by external parameters, opening pathways for experimentation and potential technological innovation. The potential influence of zero-point energy also inspires philosophical reflection. It challenges the classical idea of emptiness, showing that space itself is a dynamic structured medium with energy and activity. In this view, nothing is not a void but a thin background of motion, potentiality, and interaction. While practical extraction of energy remains beyond current capabilities, the existence of this ever-present activity reshapes our understanding of reality, revealing a universe in which the vacuum itself participates in shaping phenomena at every scale. From an applied perspective, future research continues to explore how the vacuum might be harnessed indirectly. Advances in quantum engineering, cavity quantum electrodynamics, and nanoscale systems provide experimental platforms where vacuum fluctuations can be controlled, amplified, or converted into measurable effects. While these endeavors do not violate quantum principles, They demonstrate that zero-point energy can be a tool for innovation in highly controlled contexts. Understanding and manipulating the vacuum's behavior could lead to new technologies in sensing, communication, and quantum computation where the subtle influence of zero-point energy is leveraged rather than extracted directly. In conclusion, zero-point energy and the quantum vacuum represent an omnipresent, irreducible source of energy that permeates all of space. While the energy cannot be extracted freely due to the constraints of quantum mechanics, its influence is profound, measurable, and technologically significant. The vacuum shapes the behavior of atoms, mediates forces, and even affects the large-scale structure of the universe. By studying these effects, scientists gain both practical insights for advanced technologies and a deeper understanding of the fundamental nature of reality. The quantum vacuum is not inert, it is a dynamic, energetic foundation of existence whose invisible vibrations continue to shape the universe in subtle and powerful ways. This